Hey everyone, Damian Benner here, one of the project leads at Zeppelin. Today we have our guest, Sergio Lerner. Sergio is co-founder and chief scientist at RSK, formerly Rootstock. Sergio has been around the cryptocurrency space for quite a long time. He's one of the most prominent figures in Bitcoin development and security. And actually, RSK is one of the most interesting projects and blockchain platforms out here, which allows smart contract development in the same way as Ethereum, but with Bitcoin merge mining and security. Now Sergio will say more about this. So we're talking live here. We have a chat where people can ask questions. We'll be answering them as you ask the questions. We'll also leave some minutes at the end if you have some particular questions that you want to ask Sergio. So Sergio, welcome. Great to have you here.
Hi, Damian. Thank you very much for the invitation. And I hope I can summarize the key features of the platform today. And so you can grasp what you can do in our platform and be ready when we launch it. So let me start with a presentation I've prepared. Let me share a screen. Okay, so here we go. Do you see the screen now?
Yeah, perfect.
Okay. So first of all, a little bit about me. Damian has presented me. Thank you very much for your presentation. But I would like just to say, well, I've been in this space, in the cryptocurrency space since 2011. And I started auditing the Bitcoin source code because my background is in computer security. But then I started helping designing new cryptocurrencies, auditing new cryptocurrencies. And since that time, I've been involved in many startups. I've been helping many startups here in Argentina, where RSK has its development headquarters. And well, these are some of the companies I've been working with in the past years. So my background is in computer security, as I said. Well, this is the list of vulnerabilities I found in Bitcoin, in Ethereum, and just to let you know that I've been involved in many of these protocols since the inception of them, and I love cryptocurrency design. So let's start with the agenda for today. So I will talk about the RSK platform, formerly known as Rootstock, and what differences the RSK platform has in terms of technology. And then we will talk about the Tumeric testnet, which is the testnet that is currently running, where you can test your applications. And I don't think we will have time, but maybe next time, in this stream or in another stream, we will talk about the future of RSK technology and what we are working on in the future. So let's get started. So first of all, I want to show a very high-level overview of the difference between several public platforms which implement the EVM compatible virtual machine. So as you know, Ethereum uses the EVM to execute smart contracts. And currently, letting aside the private implementation, the private blockchain, there are three competing public implementations of the EVM. One is Counterparty, which I'm not sure is currently active, but the source code is there. And then, of course, is Ethereum, and then RSK. So the first thing I want to talk about is the average confirmation time, and that is the average block interval. So in Counterparty, because this is a protocol which is embedded as an upper layer over Bitcoin, of course, we have the 10 minutes block interval. In the case of Ethereum, we have currently approximately a 15 seconds block interval. And Ethereum allows this by using the ghost protocol, which is a protocol that it's able to weight the blockchains in a specific way to reduce the number of stay blocks. And in case of RSK, we have put this block interval down to 10 seconds. And we do this by using a combination of a protocol called DCore plus the Ghost protocol. And in terms of the fairness for mining, there are several attacks that have been documented in several papers. One regarding selfish mining and my own investigation, my own research about anti-mining in Ethereum. So these papers state that there are flaws in some of these protocols, including Bitcoin's protocol. So the actual security threshold in Bitcoin is about 33%. So a miner that controls 33% and controls a higher, has a very good connectivity with the network, can actually increase its margin against the honest miners. In case of Ethereum, the theoretical point where miners get an advantage by mining uncles instead of mining blocks in the main chain, it's about 12%. So this is a flaw in Ethereum mining protocol, which will be probably solved when they switch to proof of stake. Well, in case of RSK, we keep the 51% security threshold by using this DCore protocol also. And in terms of denial of service protection, for instance, counterparty has done. Basically, they cannot control how many transactions are included in a block. And in case of Ethereum, well, there is some control based on the gas limit, as you know. But again, miners can abuse this gas limit by putting in a block transaction that have zero gas price. So that allows them to basically consume resources, consume storage, and not pay for that storage unless if there are no transactions in the backlog. In case of RSK, we have a minimum gas price which is voted by the miners. So actually, a majority of the miners are required to attack the network by mining transactions with a zero gas price. And the incentives for mining are different in each platform. In case of Ethereum, well, the ETH miners are incentivized, but soon Ethereum will switch to proof of stake. So we actually don't know much about the future of Ethereum in the proof of stake era. In case of RSK, well, we do merge mining, and as I will explain later, merge mining is a way that allows Bitcoin miners to profit and secure their RSK network. And the integration with Bitcoin, that's something that is very common requirement. It's very different in three platforms. In case of counterparty, this is an overlay protocol, so it's very easy to transfer funds back and forth, Bitcoin and counterparty assets. In Ethereum, there is an interesting project that is called BTC Relay that provides an SPV wallet or SPV blockchain embedded in Ethereum. Well, but this is still in development, and also it works by giving incentives to maintain this SPV node, which are, and it's unclear to me what will be those incentives. Well, in terms of, in case of RSK, as we will see later, we have this sidechain, and the sidechain basically allows to move funds from Bitcoin to RSK network by just sending Bitcoins to a special Exodus address, and then send them back automatically at any other time. But at the same time, the same smart contract that manages this bridge between Bitcoin and RSK also provides SPV verification service. So actually you can, from a smart contract in the RSK platform, you can verify that a transaction in Bitcoin has taken place by requesting confirmation headers on top of the transaction. And well, the future of these blockchains is depends on the plans of the different development groups on what they will do to scale blockchains. And in case of Ethereum, the Ethereum developers are focused on sharding, which is a technique to split the blockchain in several different blockchains and then combine these blockchains together. And at RSK, we have taken a different approach. And so we've tackled the problem by splitting the problem into the problem of storage scalability, the problem of storing the blockchain, and the problem of computation. How do we achieve a much higher number of computation, much higher number of transactions per second? And so we do this by two different techniques. We do blockchain scalability by partitioning the blockchain into pieces, into shards. So every node does not need to have the full copy of the blockchain. And we scale computation based on scheduling the transactions to be processed in a block, so they can be actually parallelized. And some of the other features that we are working on and the different development teams are working on are here. For example, confidential transactions. There is an interesting project to port set cash over Ethereum. This is the project Alchemy. And we have our own project ongoing to implement ApeCoin, which is an anonymization layer on top of our RSK. Well, there are many interesting features. I will skip just to go to more interesting stuff about how RSK works. And if you have any question about this chart, send it to me. Okay, so basically now I will explain the main features of RSK. So we have security and usability improvements, which are interesting for smart contract developers, which are already used to Ethereum. We have the EVM compatible smart contracts execution in VM to Bitcoin that allow us to send and receive Bitcoins from the Bitcoin blockchain. We have the merge mining engine that allows us to use the Bitcoin miners to secure the RSK network. We have the RSK Federation, which is a group of renowned companies in the ecosystem that help secure the network. And then we have, of course, the RSK network, which also has some interesting new features. So let's start with security and usability improvements. So the first thing we did is adding code versioning to the platform. So we can actually support Ethereum contracts and be fully compatible, but at the same time, we can support new scripting systems, new VMs, by just adding a small header to our contracts. So we can be backwards compatible, and also we can implement the new features of our platform. This is just a description of the new header. So we've made some improvements in terms of security, and one of the problems that we detected is that many of the contracts that were deployed failed because of very small bugs in the code that could have been prevented if there were an easy system to upgrade contracts. Ethereum already has a way to upgrade contracts using the delegated call opcode, but essentially the compilers do not support it, and it's harder to create contracts using delegate call. So basically nobody has done that. So we created a very easy new opcode, which is code replace, that allows you to change the code of any contract that implements these features in the first place by a very simple opcode. So if you want to allow your contract to implement, to be able to replace the code, then you can provide, as this example here, you can provide a method, a public method, where you receive the new code and you restrict the who's allowed to upgrade the code. For instance, here we have the modificator only owner, and then we basically just replace the code. And if you want to restrict this to several parties or a multi-signature, or make this only available for a limited period of time, well, you can just create a modifier for the method to restrict access to this opcode as you like. Also, to increase the security, we've implemented a specific send opcode, and the send opcode is actually similar to a call opcode, but it just prevents recursion. So again, you can very easily prevent most of the bugs that have been discovered in the Ethereum VM. Also, for example, to increase the speed of RSA signature verification, we've added a native contract to do modular exponentiations. And this helps, for instance, Oracle and Sergio, which are based on verifying TLS signatures, and several other use cases. And one of the things that we have to deal with is that our blockchain has no subsidy. And I think we are the first blockchain, public blockchain, who has to really deal with this problem. And to deal with this problem, we had to create a synthetic subsidy based on smoothing the transaction fees over several blocks. And there was a paper recently that discusses the problems of subsidy-free blockchains. So this is one of the measures we've taken to prevent those problems. Also, to prevent uncle mining, which is a problem that exists in Ethereum, we use the GCAR protocol. And as I said before, we have a negotiated or voted minimum gas cost, so that most of the spam attacks cannot be performed against our network. One of the things we added to prevent long-term impact of spam in the contract state is by requiring storage rent. So storage rent basically allows periodic payments for the amount of storage a contract requires. So here we have the simple equation where the rent to be paid is proportional to the memory size consumed by the contract, a constant, which is the rent cost, and the difference is between the last time the contract was written, the state was changed, and the current time of the message that it's communicating with the contract. So this is an additional cost that messages in our platform pay in order to prevent the future bloat of the state of the network, and also this allows in the future much higher scalability. So what happens when a contract does not pay the rent? Well, what we do is we hibernate the contract. And hibernation is much softer than killing the contract. So by hibernating the contract, we reduce all contract persistent storage, including the code and the memory, into a single hash. So it's not that you lose control of your contract or you lose the funds, but basically the blockchain, the state of the blockchain cleans itself, heals itself. So if you want to access your data, access your contract several years in the future, you will have to provide that information again to the blockchain in order to recover your account state. We have simplified the structures of the blockchain as compared with Ethereum. Ethereum has a very complex trie structure, which is radix 16. And that is not optimum in terms of FPV proofs. And also, Ethereum uses different tries for the storage of each contract and the storage of accounts. And we have created a simplified binary try which stores in the same tree account states, contract states, and the accounts of these systems in a single state. So this allows RSK to have a unified cache. So basically, the whole handling of the storage of the state is highly simplified.
Sergio, we have here one question from Federico Bond that's asking, what's the difference between code copy and code replace opcodes? Is this the result of arbitrary limitations in the original Ethereum design?
You mean delegate call, and I don't know any opcode called code copy. Code copy I think code copy is to copy the code from another contract. Is that correct? Yeah. So basically, with code copy, I think you can grab the code of any other contract, but that not allows you to replace your own code. It's just to inspect the code of other contract. What we use to do this upgrading of contract is delegate call. So delegate call calls another contract using this other contract code, but keeps the memory which is being used by the contract to the same memory of the caller. So you can create proxy contracts that can allow this upgrade mechanism. But because of the way contracts pass arguments back and forth, it's not so easy to create a generic proxy contract. So basically, you have to know the argument sizes, which complicates things. Code replace is very simple. It's basically just replaces the code of the contract. Did I answer your question? Well, I cannot.
We don't know. Hope we did. Anyway, Federico, if you want to ask again, feel free to do.
Yeah, please. Okay. So the RSK VM, is based on the Ethereum VM in the sense that it's fully compatible. But we have implemented in the Tumeric, in the testnet, an interpreted VM, which is 6 times faster than Ethereum J and Geth VMs as of June 2016. And approximately each instruction in a computational benchmark takes 200 nanoseconds, at least in my own computer, and that allows you to process 5 million instructions per second. And so basically, by creating this VM that is faster than Ethereum VM, we can actually lower the cost of computation in our platform. And in the next release that are in the works, we will be adding just-in-time compiling and bytecode retargeting. And if I have time, I will talk more about this later. So the way that we created the node is very similar to the Ethereum node in the sense that we provide a Web3 compatible interface. So all the layers that are up the Web3 compatible interface, like the JavaScript bridge, the Web3 application, Solidity compiler, Semper compiler, everything works on our platform. Developed a front end for your contract. Well, and that front end communicates with your Geth node using Web3. Well, you can very easily port that to the RSK node because we've provided the same interface for you. One of the most interesting features of the RSK platform is the two-way peg. So the two-way peg is a system that allows you to lock funds, lock Bitcoins in the Bitcoin blockchain, and unlock them in the secondary chain. In this case, the RSK chain. So there are many ways to achieve this lock. Basically, just the property you need to provide is that the funds, of course, cannot be unlocked in both blockchains at the same time. So magic that controls access to the Bitcoin, so that when Bitcoins are locked in one of the blockchains, they cannot be at the same time unlocked in the other blockchain. So there are several ways to achieve this. The most simple way to do this is by just having a single custodian of the funds that are transferred. So this will be completely centralized, where a single party holds all the Bitcoins and releases the secondary blockchain tokens, which in case of our platform are the smart Bitcoins. And again, when in the secondary blockchain, the funds are sent back to this custodian, the funds are released in Bitcoin blockchain. Of course, this is undesirable because this is completely centralized. A little improvement over this is having a multi-signature where a federation controls those funds, but still it's a point of centralization. Then you can actually soft fork Bitcoin to allow sidechains, or best known as SPV sidechains. So in the case of a sidechain, what you do is you provide the secondary blockchain an SPV proof that proves that some transaction in the Bitcoin blockchain has been mined. So you provide this SPV proof I will talk more about later, and a set of confirmation headers. And that's enough for the secondary blockchain to understand that those funds have been locked in Bitcoin. To do the opposite, to allow Bitcoin to understand that some funds have been locked in the secondary blockchain, you need new opcodes. Basically, these are the opcodes that Blockstream has designed in the Elements blockchain. The withdrawal proof verify and reorg proof verify. And the problem with this approach is that it requires a software, but also it only allows you to understand the consensus of a blockchain which uses the same model, the same UTXO model as Bitcoin. So it's quite limited. And a more interesting approach that was created afterwards was the drive chain. In the drive chain approach, the Bitcoin miners are able to acknowledge the state of a secondary blockchain, and when most of them agree on the state of this secondary blockchain, they allow the funds to be transferred to the required party. So the miners themselves are custodians of the funds that are transferred. Even a more secure approach is the combination of a drive chain and a federation. So basically, you have the miners that have custody on these funds, but at the same time, the federators provide signatures so that the funds can only be moved if both of them agree that the funds should be moved. So this is, of course, this is the single custodian case. It's very easy. There is someone in the middle which controls everything. I will just skip this. This is the multi-party custody where many notaries must agree to sign a transaction to move funds from one blockchain to the other. And to explain more about the SPV sidechain, I will explain SPV proofs. And probably you already know what an SPV proof is, but for those who still do not, I will explain. So Bitcoin uses a Merkle tree, an authenticated data structure that is able to prove membership of a transaction in the block with very short messages. So a Merkle tree is constructed by taking all the transactions and hashing them in pairs until a single hash is obtained. That is the root hash. So if you take a single transaction, for instance, the generation transaction in this case, and you complement that information with the complementary hashes that build the branch from the generation transaction to the Merkle root, which is, in this case are D2, DB, and DY, then you can build a short proof that this generation transaction is part of the block. And this is called an SPB proof. Because of mining, during mining, the transaction Merkle tree root hash is included in the block header. So basically, you can prove that any transaction that is part of a block, you can prove that with a message that is very short. So an SPB sidechain works by allowing the secondary blockchain in this here in this graph, it's in the right, to receive these SPB proofs, and then there's a reorganization period, which is wait, where miners or other users can send proofs that this SPB proof has been reorganized in the Bitcoin blockchain. So until this period has passed and several confirmation blocks have been recorded, for example, 100 confirmation blocks, then the funds are released in the secondary blockchain. And again, the same you can do in the Bitcoin blockchain. In derived chains, it's a very interesting approach, because when you have merge mining and you are trusting the Bitcoin miners to secure the secondary blockchain, then you can give them a little bit more power, but make this bridge a lot more decentralized. So we created a business improvement proposal, which you can follow in this link. We propose a new opcode, which is called acknowledge count, that allows you to count acknowledges from the Bitcoin miners until you get a certain threshold that guarantee that a certain event has occurred in the secondary blockchain. So in this graph, I show how a derived chain works, and so you have a transaction that is. I will talk about the return trip here. So basically, there is a transaction that appears in the secondary blockchain, and that transaction says, okay, I want to send funds back to the Bitcoin blockchain to a certain address. And from that point on, the miners include in a block, in a Bitcoin block, a proposal to do that transaction. And after, during a number of blocks, they acknowledge that they agree on the state of that proposal in the secondary blockchain. Similar to votes, but these are not actually human votes, but automatic acknowledges of the miners. And when a number of these acknowledges have been collected, then automatically the transaction becomes enabled in the Bitcoin blockchain. So RSK uses a hybrid method, and because we have smart contracts on the secondary blockchain, we can create very easily this bridge smart contract, which receives SPB proofs and handles everything related to releasing the funds in the secondary blockchain. But in the Bitcoin side, we don't have this functionality yet, this SPB sidechain functionality. So we've implemented a combination of a derived chain and a federation of notaries. Of course, since we cannot implement the derived chain right away, in the first release we will be using a federation of renowned parties to do this job. But we hope that in the near future, the derived chain BIP is merged into Bitcoin, and we can actually have the two methods to provide higher security and more decentralization. So we've talked a little bit about this RSK Federation, and the RSK Federation is a set of companies, renowned companies on the Bitcoin ecosystem that span the globe. They are not located in a central geography. They have no central control, and they maintain this multi-signature address that holds the bitcoins that are transferred to the RSK platform. Also, in the future, they will be providing different services to the platform, such as oracle service, signed checkpoints, and signed states for fast bootstrapping of nodes. Well, I will skip the details of the method of how the federation works to help handling this breach contract. Maybe in another time. And then I will switch to the merge mining. Merge mining is the process where Bitcoin miners can mine the RSK network, the RSK blockchain, and Bitcoin at the same time. So for merge mining to work, we need to insert in some part of the transaction, in some part of the block, block hash of the RSK block that is being mined. So this hash, this RSK tag, can be included in several places. So two places are very common to include merge mining tags. One of these places is the Coinbase field. The Coinbase field is the Coinbase transaction, or also called the generation transaction, is the first transaction of the Bitcoin blockchain. And because the script sig of this transaction is not used, it is free for miners to fill with anything they want, except the blockade, which is by consensus inserted there. So there is space for extra data, and the RSK tag, which contains the RSK block string, followed by the hash of the RSK block. This information is stored in this Coinbase field. This is one of the possibilities. The platform also allows this tag to be stored in any output of the Coinbase transaction if it is after an out return. So if you don't want to embed this tag in the Coinbase, you can just add an output to your generation transaction and add the tag after that. So to summarize, the proof that RSK requires to accept a proof of work contains the generation transaction of Bitcoin that contains the embedded here, the embedded tag, and these squares in blue, which are the complementary nodes of the Merkle tree that consists of the SPP proof. So we have focused on providing the Bitcoin merge miners the tools and the software to do merge mining with their own software. So we created implementation of the merge mining software for CT Pool, LOE Pool, Slash Pool, and CoinServe, several implementations of mining pool software. So probably you already know what a mining pool is, but just want to say that mining pool collects shares from clients, from workers. And those shares are Bitcoin blocks solved at a very low difficulty, and they are used for accounting how much hashing power has been contributed by each of the workers. So essentially, these shares are contributed to the mining pool, and the mining pool updates these internal ledgers for accounting. And when one of these shares has a greater difficulty than the RSK network difficulty, then this share is submitted to the RSK node, and that share constitutes a proof of work for the RSK blockchain. So that's a new block of the RSK blockchain. If it happens that the share difficulty is over the Bitcoin threshold, then that share is contributed to the Bitcoin node as a Bitcoin block, but also as an RSK node, because it also surpasses the RSK difficulty. To give this is the basic structure of the merge mining software. It communicates basically with Bitcoin D and with the RSK daemon at the same time. And these are the approximate difficulties of each of the blocks. Of course, the one with less difficulty is the share, which in this case, in this example, it's 2 to the 51 hashes required. Then you have the RSK shares, which, assuming 100% merge mining, are about 2 to the 62 operations. And while Bitcoin blocks obviously are much higher difficulty. Generally, what happens is that the share difficulty is less than the RSK difficulty, and the RSK difficulty is less than the Bitcoin difficulty.
Sergio,
yeah,
we have a question here from John Marlin. He's asking, how long will the transfer from one chain to the other take? I guess he's referring to drive chains or side chains.
Yeah. So essentially, you need to be able to assure that there will be no rollback. There will be no reorganization of the Bitcoin blockchain that will allow a double spend. But if that were the case, you could unlock funds in Bitcoin and at the same time unlock them in RSK. So we need at least 100 block confirmations to go from one side to the other. There is the possibility to use dynamic number of blocks. If you are transferring a very low amount, the system could adapt and allow you to transfer using a less number of confirmation, but essentially you will need about 100 blocks of Bitcoin confirmation. So you will have to wait approximately a day. That doesn't mean that transferring from RSK to Bitcoin and vice versa, it's not possible to do that instantaneously, because there will be liquidity providers, exchanges like Shapeshift, that will allow you to transfer these much faster. And also, the bridge contract in the RSK network allows you to do very easily peer-to-peer exchanges, because you can just create a small contract that only releases smart bitcoins if a transaction that transfers bitcoins has occurred in the Bitcoin blockchain. So you can very easily also create peer-to-peer exchanges almost instantaneously with very little confirmations. I will skip talking about the network. So what we have working currently is the Tumeric testnet. The Tumeric testnet has 1.5 petahash of merge mining against the Bitcoin mainnet or the Bitcoin testnet currently. And we are already working with 30% of the Bitcoin miners, so they can do merge mining when we release the production-ready platform. And more than 50% have expressed the support for the project. So we are expecting to have a lot of engagement in merge mining in the future. Also, the federation has grown to more than 20 very important companies in the Bitcoin ecosystem that will take part of this multi-signature in the beginning to secure the funds. So even if we will suggest that in the beginning the users do not transfer high amounts of funds, they will be pretty secure by all these companies having a share, a key part of this multi-signature. As already talked, we have this high performance implementation of the software, of the mining pool software already working. And if you want to test your applications in the Tumeric testnet, we have a block explorer, stat sites, an SBTC faucet, and multi-currency, multi-platform wallet, which is JAX, that you can use to test your contracts using smart bitcoins, and much more utilities that will be ready for the launch of the platform. So if you want to have an early access to the Tumeric testnet, You can fill the form in the rsk.co website, and we will give you access to a node online, so you can just very easily start working and start testing your smart contracts against a node that's it's already in the cloud. So here are some screenshots of the different services we are running, and if you see similarities with Ethereum services, that is because we have just taken open source projects from Ethereum ecosystem and just ported them very easily to the RSK network. Okay. Also, we have several companies already porting their products to our platform. If you want to know more about these companies. And the RSK roadmap is, we will launch the first release of the public platform in May and 2017, this year. So that release is called named Ginger. And also we have a planned hard fork for the end of 2017, which is called Bamboo, that we will be adding a lot more interesting features regarding scalability we are working on. And I hope that in next time I will talk more about Bamboo and the future improvements of the platform. Okay, if you want me to go on, please. I can go on, but I think that I've already taken a lot of your time. So any questions, I'd be glad to answer.
Awesome, Sergio, great talk. Thank you so much. For the people watching, if you want to ask questions, now it's the moment. There's one question here from Federico Bond asking if there are any plans for an RSK-supported Solidity compiler.
Yes, we will support. Yeah, we will provide a Solidity compiler that that is compliant with our platform. But most of the enhancement of our platform can be accessed by native contracts that you can already use in the current version of Solidity compiler. So we have the patches to support the new opcodes, but you can actually use many of the features like the bridge contract just by declaring a contract, the API interface, and interacting with the native contract.
Perfect. Yeah, I think especially for the Zeppelin community, you know, maybe signing up for the Tumeric Testnet network would be very interesting. Because they're really developing a bunch of smart contracts. For those who don't know about Zeppelin, Zeppelin is an open source framework to build secure smart contracts, like a common repository of vetted and reusable components to build decentralized applications in the Solidity language. Sergio, I have one question from the beginning of your talk.
Yes.
When you talk about the difference between RSK and Ethereum, can you explain, like in a short summary, because you mentioned a lot of things where RSK is much better than Ethereum on counterparty, but what of those things are really better? You know, can Ethereum improve in the short, medium, or long term? And what are things that RSK is better because in terms of design, Ethereum will not be able to catch up with that?
I think that the Ethereum community is very flexible. So I think that most of the things we do, they can also do. I'm not saying we have any exclusive feature. Some things require quite important hard forks. So for instance, the change we've made to the basic data structure of that hold the state, I think that will be very, very, very difficult for Ethereum to change without actually porting every single contract into this new data structure. So that would be probably one thing that Ethereum, it's very costly for Ethereum to do. Most soft codes that we've implemented, they can also implement. There are certain things that are not so easy to hard fork in Ethereum. For instance, we have a different economic model. We have this storage rent. So it's very difficult for an Ethereum developer that has actually signed for a certain contract with the platform that that contract with the platform is changed, and then they have to pay, for instance, a new fees, because when the community engage with the platform, they signed, there's an agreement between the users and the platform, so what they can expect from the platform. So, for instance, that's another thing that would be very, very hard for the theme community to implement if they wish.
I see. Perfect. Thanks for the answer, Sergio. Yeah, thank you so much for talking. It was very interesting learning more about RSK. We're really excited about the Tumeric testnet and Ginger and Bamboo eventually to start building stuff and smart contracts on top of RSK. So
thank you very much. Thank you very much, Damian. And thank you for all that watching now and will watch in the future. And if you want to test your application, go to our webpage and we will provide you everything you need just to get started very easily. Thank you very much.
Bye-bye.
Bye.